Do we have an interpretation for the eigenvalues yet? For the orbit Jacobian eigenvalues?
One thing we know is we have, the only thing that helps us because we're used to evolution of time, we have Hill's formula.
Yeah.
So we know that the product should be exponential with the period of Bravais lattice.
Right.
So that means that each one of them should be nth root of that exponential. That means each one of them should be some kind of constant size, right? Because it's only the product that grows exponentially. So if you take a logarithm divided by n, we expect that the mean of that should be some constant number. Now we have the intuition what it means is because we have the interpretation, we have Bernoulli map and cat map in which the diagonal is constant. So they all have the same value, right? So that looks like it's a mean stretching rate, but it fluctuates because as you go around the nonlinear place, you stretch and shrink it. So somehow the eigenvalues are related to what's called Floquet exponent in some way, because that's what Floquet exponent is. If the leading multiplier of your Jacobian is growing exponentially, then if you take its logarithm, divide it, and that's why you also do this for escape rate, take logarithm, divide by number of steps, that should go to some limit. So, so we have some kind of understanding, but what makes it a little bit awkward, and that has to do what Han has done on reciprocal lattice, is that you're not actually looking at the matrix, but you're looking at 1 minus the matrix. And that actually means a lot because it means that it's not multiplicative. The matrix itself is multiplicative, but 1 minus the matrix is not. It just isn't. So then you have to think about what it means. But what it means, 1 minus is really great because the expanding eigenvalues overwhelm 1. So if you go to longer cycles, they start looking more and more like you're just looking at the Jacobian, but only for the expanding eigenvalues. The marginal eigenvalues you have to really be careful about because as you did in your presentation, 1 minus 1, that's bad news. There's no expansion or contraction, so that's really tough. Now, what's nice about this form 1 minus is that there are many, or maybe infinitely many, in fluids of contracting eigenvalues, but they're all small. So they, 1 overwhelms them. So they show up not in a leading order, but they show up in next to leading order when you look at correlations. So we know that. So we know something about the size of eigenvalues for orbit Jacobian, because we know explicitly examples, 2 of them that we use, Bernoulli and the cat, temporal cat, in which stretching is uniform every place. So we know that this really, we're computing mean stretching. So that's the first thing. Now, next thing you have to think about signs. And these guys have signs, and I have trouble with that. So the sign, there are signs, for example, in Anon and in 5-4 theory, it says the value of field, the lattice side is either positive or negative. We use it for phi cube theory, we use it to have symbolic dynamics. For 5-4, we use it because we have plus, 0, minus, so we use the signs. So that is what happens to the lattice state. But orbit Jacobian eigenvalues live on reciprocal lattice because you have to take discrete Fourier transform of a lattice state to get orbit Jacobian matrix diagonalized. Now here I'm lost. I don't know how it works because everything that's in reciprocal space is an average over lattice state weighted by e to the phi or cosine theta or whatever, They have plus and minus sign, but I don't know what the hell that means. Except because we have this anti-integrable limit, we have good intuition about them when the stretching factor gets very strong, or this mu squared, the mass gets heavy. The potential is so heavy that Laplace doesn't matter so much anymore. So we have some idea about science, but I don't get it. What can I say? So I hope you get it. And then there's all this other stuff. They have every eigenvalue has eigenvector. What the hell do these eigenvectors mean? Now, these eigenvectors, it's easier to understand on the reciprocal lattice, and you have some intuition from your knowledge of electrodynamics, wave mechanics, quantum mechanics. You know that some eigenvectors with a small coefficient, k0, 1, 2, 3, they are the long wavelength variation. So they're small. The zero is just constant, but the other guys describe some kind of fluctuations, some kind of waves on reciprocal lattice. And, might be good if we understand that, so there's some understanding that these guys should be describing what kind of long range correlation you have at k is small. And when k is large, they describe very wiggly stuff. But I don't know. That's about all I know. Han, do you know something else I haven't mentioned?
If we're doing some computation using the gradient descent or Newton's method, when we compute the derivative, there might be a Orbit Jacobian matrix appear somewhere.
Yeah, Newton is the Orbit Jacobian matrix. That's how we understood it first.